Welcome back. Today's lecture is about Hadoop and HDFS. So I will firstly give a brief introduction about Hadoop, and I will introduce HDFS in a more detailed fashion. So basically I will talk about the architecture of HDFS, some basic concepts, and how things works in HDFS. For example, how do we read and write in HDFS? Also, I will talk about how does HDFS guarantee the reliability of data. So let's start from what is Hadoop. So Hadoop is an open source software framework. It's a framework that stores big data in a distributed manner, processes big data parallelly, and builds on large clusters of commodity hardware. Here, the first two sentences describe the main purpose of Hadoop, which are storing big data and processing big data. It also shows the major feature of Hadoop that it does both things in a distributed manner. Okay, the third sentence describes the hardware requirements of Hadoop. So all you need is a large number of commodity PC. You don't need some fancy supercomputers or whatever. The history of Hadoop closely related to two Google's paper. One is Google's file system, and another is MapReduce. So in 2003, Dog Cutting launches a project named Nudge. This project is used to handle billions of searches and indexing millions of web pages. So later, in October of 2003, Google releases the paper with a Google file system. And in December of 2004, Google releases paper with MapReduce. So in 2005, Nudge used GFS and MapReduce to perform operations. And in 2006, Yahoo created this project called Hadoop based on GFS and MapReduce with Dog Cutting and his team. So Hadoop, the name comes from Dog Cutting's son's toy elephant. So that's why the icon is a cute elephant here. And it was pointing out that unlike Google's technology of GFS, which is not open sourced, Hadoop is a fully open sourced project. You might still remember the 3 V's of big data when we introduced the big data. So volume, velocity, and variety. And Hadoop can handle these 3 V's very well. So for volume, Hadoop is scalable to petabytes or more data easily because it uses a large clusters of computers here. And for velocity, because Hadoop offering parallel data processing, so the process speed is quite fast. And for storing, for variety, in Hadoop, you can store in all kinds of data, structured, semi-structured, or unstructured data. It's unlike a database manager system. So in Hadoop, or more specifically in HDFS, there's no pre-dumping schema validation or whatever. So you can store all kinds of data you like. And in today's class, we will focus more on volume issue, while when we introduce MapReduce, we will focus more on this velocity issue. All right, so that is Hadoop. So Hadoop offers HDFS, which is redundant and fault-tolerant data storage, and MapReduce, which is a parallel computation framework, and Yarn for job coordination and scheduling. So all these modules in Hadoop are designed with a fundamental assumption that hardware failures are common occurrences and should be automatically handled by the framework. So, for example, you will see in today's lecture in HDFS how we deal with these hardware failures and to make sure the fault tolerant of data storage. And with Hadoop, programmers no longer need to worry about issues like where the file is located, or how to handle failures and data loss, or how to divide computation that's in MapReduce, and how to program for scaling. So all these things, the framework handled for them. So instead, the programmers can focus on their own tasks and design the program within the framework. So Hadoop ecosystem. Now, I mean, it's 14 years later, no longer Hadoop version 1. We are here Hadoop v3. So basically, we have a whole ecosystem of Hadoop. But the core part is Hadoop distributed file system, which is HDFS, will be introduced today. This component store different types of large data sets, like we have mentioned before, including structured data, semi-structured data, unstructured data. It helps us in storing our data across various nodes and maintaining the log file about the stored data. And MapReduce. MapReduce is a software framework which helps in writing applications that processes large data sets using distributed and parallel algorithms inside Hadoop environment. So while we will introduce MapReduce in detail, I think in the following weeks, 1 or 2 weeks, here I just briefly introduce the idea of MapReduce. So basically you've got two functions, the map function and the reduce function. The map function performs actions like filtering, grouping, and sorting, while the reduce function aggregates and summarizes the result produced by map function. And the result generated by map function is a key value pair. So it's a pair of key and value, which acts as the input of reduce function. So your design of a program should fall into this MapReduce framework. All right, Yarn, which stands for yet another source negotiator. Yarn is available from Hadoop version 2.0, and it is the brain of your Hadoop ecosystem. It allocates resources and schedules tasks for all the processing activities. Apart from this core component of Hadoop, there are a bunch of additional software packages. So here, I just list a few of them, but there are more. And if you are interested, you can use Google or Wikipedia to further explore them. So basically, we have Pig, which is a high-level platform for creating programs that run on Apache Hadoop. Pig offers an ad hoc way of creating and executing MapReduce jobs on very large datasets. And Hive. Hive is created by Facebook. It is a data warehousing component. And Hive performs reading, writing, and managing large datasets in a distributed environment using SQL-like interface. Spark. Spark is a framework for real-time data analytics in a distributed computing environment. It executes in-memory computations to increase speed of data processing over MapReduce. So in MapReduce, in HDFS-based MapReduce, the computation is based on disk I/O level, and in MapReduce, it's in memory level. We will introduce more about Spark later. And HBase. HBase is an open source non-relational distributed database. In other words, it is a non-SQL database, if you still remember. We have introduced in week 1. So if we're handling a large data set while retrieving a small amount of data, we need HBase. It supports all types of data, provides big table-like capabilities. And big table is Google's paper in 2006. So it's also a core component of how Google's big data processing ecosystem. Now let's see the architecture of Hadoop, or the main idea of Hadoop. So this is called a master-slave architecture, but I would rather call it a manager-worker architecture. So basically the same thing. Okay, just think of this scenario where we have a worker, which is, let's say it's you, okay, and there are 3 tasks. While for each task, you would need 1 hour to finish it. So you would have 1 hour for task 1, and 1 hour for task 2, and 1 hour for task 3. Since you are the only worker here, so you need 1 + 1 + 1 equals to 3 hours to finish all the tasks. So apparently you are quite exhausted of doing so. And so let's put salary issues aside. So you think, okay, I don't want to do all these tasks. So you decide to build a company, and you become a manager. And you hire 3 workers, A, B, and C. Ask them to do the tasks for you. So let's assume that for all the workers have the same efficiency as you. So basically, worker A need 1 hour to finish task 1, and 1 hour for worker B, and 1 hour for worker 3. Okay, you look at the arrows here. So previously the tasks is assigned to you, and now you assign the tasks to the workers. So if worker A and B and C, they work simultaneously, all you need is 1 hour, and you've got all the tasks done. So that is the beauty of distributing. So everything looks fine except one thing. The workers have their own rights. They can ask for a leave. For example, worker C, he decided to take an annual leave someday, and his task, there's no one can complete his task. So here comes the problem, because you've got a task 3 where no one is gonna finish it. Well, you are the manager. You don't want to do it by yourself. So what should you do? you can assign task 3 to either of the other 2 workers here. For example, you can assign task 3 to worker 1 to worker A as well. So in this case, when worker A is on leave, the worker A will do task 1 and 3, and worker B will do task 2, so all the tasks will be done. So in order to make the whole thing work systematically, you decide to assign each task to 2 workers. For example, worker A for task 1 and 2, B for task 2 and 3, and C for tasks 3 and 1. So in this case, any one of them on leave, you will still have all the tasks that have workers working on it. For example, C is on leave, you still got task 3 on B can work on it. So let's summarize the idea here. So basically, in order to improve the efficiency, you distribute tasks to different workers. In Hadoop, the workers are computers, or more specifically, commodity computers. So these workers, they could be on leave, like your computers may fail or doesn't work. In order to cope with that scenario, the idea is to assign tasks to multiple workers. Like you will later see in HDFS, how we assign how we generate replications of blocks and store them on different nodes. So in this case, all the tasks can be finished, even some of the workers are on leave, or in Hadoop, some computers are not working. So now let's look at HDFS, which stands for Hadoop Distributed File Systems. So HDFS is a file system that follows master-slave architecture, allows us to store data over multiple nodes or machines. It also allows multiple users to access data, and okay, it's just like a file system in your PC or except the only difference is that in case of HDFS, you store data in multiple machines rather than in your own PC, you store data in that single machine. So that's the only difference here. And for the users, they will just feel like all the data is stored in his own machine, or we call the client, although the data are actually stored across the network. So for example, imagine there are several computers, let's say 5 computers, while each of them has a hard drive of 1 terabyte. So here, this is you. And okay, if you install Hadoop as a platform on top of all these computers, then you will get HDFS as a storage service, and every computer contributes their capacity of storage to you for store any kind of data. So basically, you can store as much as 5 terabytes of data using all these computers. Well, actually, you are not, because of the replication thing. You probably can only store 5/3 terabytes. Well, anyway, we will introduce this later. So with HDFS, you can store you can store more than 1 terabytes of data. Although your computer, it only have a hard drive of, for example, 1 terabytes. So you can store more than that with HDFS. So HDFS supports distributed storage, which is what we've mentioned here. It supports distributed computation, which is MapReduce, which will be introduced next week, I guess. Yeah, and it supports horizontal scalability. So what is horizontal scalability? Here is the example. So in contrast to horizontal scaling, it's vertical scaling, right? So let's look at what is vertical scaling first. So in vertical scaling, you increase the hardware capacity of your system. For example, you buy a new RAM or CPU or hard drive, and you add it to your existing system, or you just update your existing computer with them, and make it more robust and powerful, have more capacity. This is vertical scaling. So in our case, there are 2 problems of vertical scaling. So one is there is always a limit to which you can increase your hardware capacity. For example, you cannot add unlimited RAM or capacity of hard drive to your computer, right? So there is always a limitation there. And in vertical scaling, if you want to update your hardware, you need to stop your machine. And this downtime, when you are stopping your systems to update your hardware, can become a challenge. I mean, at least your computer doesn't work at that time, and the services need to stop as well. So in case of horizontal scaling, as shown in the right part, you add more nodes to existing cluster instead of increasing the hardware capacity of individual machines. So before you have 5 computers, let's say, and now you have 10. That is a horizontal scaling. So in this case, there is no limit, right? You can add as many machines as you want, and you don't need to stop the existing machines in order to scaling up. You can add more machines on the go without stopping the system. And also, these computers, although in the figure here they are the same, but they are not necessarily to be the same. I mean, you can add more powerful computers, and you can also add less powerful machines if you like. But either way, you have scaled up your whole system. That is the beauty of horizontal scaling, and HDFS actually supports such kind of scaling because of its architecture. So here is the architecture of HDFS. So we have a name node, a secondary name node, and data node. You can think them all as machines. And HDFS client could also be a machine. That is the machine that you are using. And files here, they are split into blocks. All these little squares, they are blocks. and the blocks are stored in data nodes. Or more specifically, the blocks are stored in the local disks of the data node. And as shown in the architecture, you can see that the client only communicate with name node, and the name node, the secondary name node, only communicate with name node as well, and name node communicates with all these data nodes, and there is no communication between any of the data nodes here. You probably have noticed a couple of other things. For example, this red block. Let's use blue here. So this blue block, it stored here and here and here. So are they the same block? Yes, they are. And we will introduce later why we do this. We will copy this blue block. Actually, we copy all the blocks for 2 more times and store them in different data nodes. And also the rack here. So a rack contains multiple data nodes. So you can think a rack it is a set of data nodes that are physically close to each other, or say they located together. So in rest of today's lecture, we're going to introduce what is name node, what is secondary name node, what is data nodes here, and how the files are turned into blocks, and how the blocks are stored in data nodes, and how, the client, there are 2 kinds of operations here. One is write, one is read. So how do we write data to the HDFS, and how do we read data from HDFS? All these things, including why we need multiple copies of the blocks. All these things are going to be covered in today's lecture. So first of all, the name node. Name node maintains and manages the blocks in the data nodes. So it acts like the master node in a master-slave architecture. So the functions of name node, including for example, records the metadata of all the files. For example, the location where the blocks are stored, the size of all the files, the permissions, and the hierarchy structure of these files, and so there are 2 files associated with the metadata and are the most important files in name node. So one is file system image, FS image, and the other is edit logs. So FS image contains the complete state of the file system's namespace ever since the start of the name node. So what is a file system namespace? So it is the tree structure of a file system. The edit logs. The edit logs contains all the recent modifications that are made to the file system with respect to the most recent FS image. For example, if a file is added in HDFS, then the name node will immediately record this in the edit log. So that is how it records each change to the metadata. Insertion or deletion. So basically in HDFS, you cannot simply update the file. You can either add the file in the system or remove the file. Okay, you cannot update it. And name node would regularly checks the status of data nodes. So the name node should know whether the data nodes are alive or not. In order to do that, the data nodes will regularly send a heartbeat message to name node. I think the default time interval is 3 seconds. So every 3 seconds, the data node will send a heartbeat message to name node, such that name node would know that the data nodes are still alive. It keeps a record of all the blocks in HDFS. For example, of where the block is located, which file the blocks belongs to, such kind of information. Okay, and if the data node fails, the name node should handle the data recovery. For example, the name node would choose the new data nodes for the new replicates and balance the disk usage and manages the communication traffics to the data nodes during this whole data recovery thing. Therefore, for data node, we would need a very high available server that manages the file system namespace and controls access to files by clients. In other words, we expect the name node is much more reliable than the other than those data nodes. So data nodes, data nodes is a commodity hardware stores the data. So it serves as a slave node in the architecture. Commodity hardware means, the data node does not to be expensive or in high quality or high availability, unlike the name node. It is good because we're going to have a lot of data nodes, and the low requirement of data nodes would help us to reduce the cost of building the whole system. So the functions of data nodes are relatively simple. So it stores the actual data, the blocks of the files, and it performs the read and write requests. Well, here I did made a mistake here. If you go back to several slides before, here in HDFS architecture, I said there is the HDFS client only communicate with name node. This is incorrect because it also communicates with data nodes via read and write data with the data nodes. Okay, so back here, that's the second function. The third one is to report the health to name node, the heartbeat, which we have already talked before. So here is a comparison between name node and data node. It may not be comprehensive, but I've listed all the things that I think is important here. So basically, the quantity of name node is 1. Well, actually more than 1 in later versions. I think in version 2.x and 3.x. But still, it's much less than the number of data nodes. Well, data nodes would have multiple, in fact, many data nodes here. The role of name node is the master, served as master, while the data nodes are served as slaves. The name node stores metadata of files, and the data node stores the blocks of files. The hardware requirement for name node we need high memory, while for data node we need high volume of hard drive. The failure rate of name node is expected to be lower, while the failure rate of data node are expected to be higher than that of name node. And the solution to handle this failure, for name node we would have a secondary name node, for example, and maybe another name node contains metadata with a remote NFS amount. For data node, the solution to handle failure is to use replications. That's basically the main differences between these two kind of nodes. As I mentioned before, the computers could fail. So when the name node failed, all the files on HDFS will be lost, because there's no way to reconstruct those files from the blocks just without the metadata in name node. For this reason, it is important to make the name node resilient to failure. The first way is to back up the files that make up the persistent state of the file system metadata. Hadoop can configure so that the name node writes its persistent state to multiple file systems. These writes are synchronous and atomic. So the usual configuration choice is to write to local disk as well as a remote NFS mount, where NFS stands for network file system. Okay. And the other way is to use a secondary name node. So secondary name node. So a secondary name node is to take checkpoints of the file system metadata present on the name node. And it is not a backup name node. It's different from name node. They have different functions and serve different purpose. So for secondary name node, the functions includes first of all, stores a copy of FS image file and edit logs. On top of that, a secondary name node periodically applies edit logs to FS image and refreshes the edit logs. If the name node is failed, file system metadata can be recovered from the last saved FS image on the secondary name node. So the main reason of periodically applies edit logs to FS image is to prevent the edit logs from becoming too large. And the secondary name node usually runs on a separate physical machine because it requires plenty of CPU and as much memory as the name node to perform this merge operation. The secondary name node indeed keeps a copy of the merged namespace image, the FS image, which can be used in the event of the name node failing. However, the state of the secondary name node lags that of the primary one, the name node. So the help of secondary name node on preventing the data loss when the total failure happens on the name node is limited. The usual way of handling this case is to copy the name node's metadata files that are on the NFS mount, copy them back, and run it as a new name node. So this figure shows the relationship between name node and secondary name node. So basically, secondary name node query for edit logs and in regular intervals. It updates the FS image with which stored in the FS image which stored in secondary name node. Update FS image with the edit logs here, and copy this one back to name node. So make sure that in such case the two FS image are the same. So as you can see that name node does not directly update FS image, or the name node only combines FS image with edit logs to get the newest status of all the files. With a secondary name node, which do this merging thing for name node in regular intervals, such that the name node can perform faster because it does not need to apply a long edit logs on the FS image to get the newest status. It can use the almost newest one from the secondary name node. All right, so far we've talked about, let's go back to here. We've talked about name node, secondary name node, and data node. They're about their functions and how the relationships between each other. Now let's look at how the files are split into blocks. So, yeah, the blocks. Okay. Block is a sequence of bytes that stores data, or you would, if you like, the smallest continuous location on your hard drive where the data is stored. The concept of block is just like those in database management system, except the block size in HDFS is much larger. All right. So data stores as a set of blocks in HDFS. We're going to talk about this later. The default block size is 128 megabytes. This is in Hadoop 2.x and Hadoop 3.x. The default value of block size is 64 megabytes in Hadoop 1.x. All right. So one file is split into multiple blocks according to the block size in HDFS. For example, if we use the default block size, 128, and assume that we have a file of 330 megabytes. All right, so the file will be split into 3 blocks. So the policy here is to make the blocks as full as possible. So, for example, we have 330 megabytes here. For one block with 128, we would have 202 megabytes left, which means we need the other block. And if we do the minus again, which left us with 74 megabytes again. So now we have already fulfilled 2 blocks, and we have 74 megabytes left, where we need the third block C here for this 74 megabytes. Now, in this case, although the block size is 128, but how many space we used in a block actually determines the file size that corresponds to the block. For example, if we see the in the computer, like the file corresponds to all these 3 blocks, their size would be 128 for 2 and 74 for 1. So as I've mentioned, the block size in HDFS are much larger than the usual block size in database managed systems. For example, in DBMS, the typical block size is within a KB. Yeah, but in HDFS, it's usually 128 MB. So why do we use this large block size in HDFS? First of all, we need to keep in mind that HDFS stores huge datasets. So the size of the datasets is huge. So let's assume that if the block size is small, let's say 4 KB like in Linux or many database management systems, then the number of blocks will be large. For example, if you have a file of 40 gigabytes, then if in HDFS, there will be 320 blocks. But if you use 4 KB as the block size, then the total number of blocks here would be 10.49 million, which is a huge number compared to 320. So the problem here is if we do have this much blocks, then we would need too much metadata for name node, while the size of the metadata has nothing to do with the size of the block, but it need to contain the information like where the blocks are allocated, with the actual size of the blocks. So if we do have 10 million blocks, this will generate a large amount of metadata and too much for the name node. And that's one thing. Another is too many blocks will bring too many seeks that affect the read speed. The read speed, okay, here the read speed actually contains 2 parts. One is the seek time, and the other is the transfer time. So for seek time, for transfer time is the total size of the file divided by the transportation speed as t. So the total size of the file would be the same, but the seek time here, because the blocks are not stored sequentially on the data nodes, it actually stored distributedly on different data nodes. So for each one of them, we need to seek where it is. So the seek time actually proportional to the number of blocks here. So basically, if you use a small size of a small block size, then you would increase the seek time by a large amount of coefficients here. So ideally, we would like that the transfer time be significantly longer than the time to seek the blocks. And also, the MapReduce, the performance of MapReduce would be harmed if we use a small block size. And here we won't say much about this. We will introduce MapReduce later. But the idea is the map task in MapReduce normally operate on one block at a time. So if you have two field tasks, say are fewer than the nodes in the cluster or the workers, because your map operation is on the block which is too small, so you would generate too few tasks. Then your jobs will run slower than they could. I mean, if you use a large block size. This is also the reason why we don't recommend to use HDFS for small files. Yeah, basically the reasons are quite similar. That's for that. Okay, so that's all for the reason of why the large block size. Okay, I think we could have a break, and anyway, it's a virtual break. But basically, this is the end of this video, and we will start